What we can do is we can visualize vibration based on video data. It's pretty cool that it's only a software because all we need as data is video data. That means you can just take any type of video, like standard formats, put it in the software, and the software will analyze it in regard of the vibration, of the deformation.
Hey everyone, it's Eamon with ipXchange at the ipXchange Studios. I'm here talking to Benjamin from gfai, and we're going to be talking about something very interesting today because they can take pictures where you can see the sound / loudness / vibration of the picture, which is kind of mind-blowing. So before we get onto that, Benjamin, would you like to just introduce yourself, what you do at gfai, and a little bit about the company and what you guys are all about?
Yeah, sure. Thanks, Eamon. I'm Benjamin from gfai Tech, as Eamon just said. I'm responsible for the sales at gfai Tech, and what we do is a lot of different things, mainly in the field of noise and vibration. We have a little bit of an interesting company structure because we are a commercial company, but we are owned by a research association, and this is a non-profit research association called gfai EV, and this is where all the research is happening, and they work on different fields, and nearly everything they do is funded by the German government or by different funds, however they can access it with different projects. And for the products which comes out of that research, we are there basically. So we are the part which commercializes and distributes the products. We produce them partly, and all the money we make goes back to research, and the research is additionally funded. So we have a very nice setup here at gfai.
Nice. So I think probably the easiest way to get started into this topic is to talk about WaveCam. So can you tell our audience what WaveCam is and what it does? Because this is, when I first saw this was the head scratcher.
Yeah. Okay. So WaveCam is a software basically, and with that software, what we can do is we can visualize vibration based on video data. It's pretty cool that it's only a software because all we need as data is video data. That means you can just take any type of video, like standard formats, put it in the software, and the software will analyze it in regard of the vibration, of the deformation. So that actually can be videos from a mobile phone, depending a little bit on what you want to look at, like especially what frequency range, because according to a certain frequency range, you need to have a certain frame per second in the camera. So sometimes you also need a high-speed camera, but depending on what you're looking at, just take the video and our software will analyze that video and will find what is actually structurally happening in whatever you're recording. So we can visualize then the displacement, the vibration.
Cool. So out of interest, if you were going to use a mobile phone camera, for example, for this, what vibration frequency can you get up to?
That depends on the mobile phone and on the frames per second. So the standard video is 30 frames per second, and it's basically Nyquist law. So you have a certain sampling frequency. In this case, it's the frames per second, and half of that is what you can visualize in the frequency range. But if you talk about mobile phones, nearly all of the mobile phones do have a slow motion mode. Some have a super slow motion mode. I know with iPhones that goes up to 240 frames per second.
Okay, so you can go up to 120 hertz.
Exactly, that would allow us to go to 120 hertz. Other smartphones like Xiaomi or Samsung, they have an ultra slow motion mode which goes up to 960 or even above 1000 frames per second.
Okay.
And that allows us to really go to 500 up to 500 hertz in the post processing or in the analysis.
Cool. So assuming that you're not using it with just a phone camera, what kind of applications would you use WaveCam for, and like the use cases?
We do have a lot of different use cases. As it is a pretty flexible method, and is really only defined on basically what kind of camera lens frame per second combination you use. There is not a real big limitation there. So the customers we have, they work a lot in R&D, because there you can, I don't know, it's very interesting normally to find out the mode shapes of certain objects like brake discs or any other structural parts where you really need to know what are the eigenfrequencies, the modes of that object. This is of course a very good use case. So a lot for mechanical and structural analysis of any type of parts. But we can also measure super small things like boards, PCB boards, something like that. For those parts, it's really relevant also to know how different parts of that board shake with different frequencies.
Okay.
Classical example is boards in cars, for example. They are constantly excited by the vibration of the car, so they really need to make sure that at a certain frequency, no part is falling off or something. So small objects, but we also measured complete buildings. Like we have examples of different skyscrapers, of the Tokyo Tower, for example.
Okay.
Some bridges, and for those objects, it's more about finding out how they vibrate for maintenance reasons. And for those really big objects, it's extremely difficult to measure displacement or vibration with conventional methods. And with our methods, it's just a question of a few minutes. So there, the advantage is really, really good. And the last big field of application is, in general, maintenance, like machine maintenance, predictive maintenance, measuring machines, like production machines, smaller machines, medium-sized to big-sized machines, or only parts of that, to see whether something in the vibration changes, indicating that something is about to break. Or you have already a problem and you don't know where it's coming from. You do a measurement and then find out where that particular vibration is coming from.
Cool. So before WaveCam, what would people need to be using to do the kind of predictive maintenance, and particularly for the large like building and bridges vibration measurement?
In general, the results we get traditionally, you could get the same things with two types of technology. The one is vibration sensors. So you place a couple of vibration sensors on your object, measure excited, or maybe it's already natural excitation, so it happens by itself. You measure that vibration, take that data, put it into a software. In that software, you need to have like geometrical information of whatever you're measuring. You need to place virtually where the sensors are placed, take in the data, and then do some post-processing to visualize what's actually going on.
So that's a lot of work.
It's a lot of work. Plus, if you think about smaller objects, like lighter objects, placing sensors sometimes is not working because you change the weight. Let's say you have a really small object and you want to find out how it's vibrating. It doesn't make sense to add a couple of vibration sensors which change the weight. Hence, it's changing the way it vibrates. This is the one approach, and the other approach is laser Doppler vibrometry. So you probably heard of that technology.
Yeah, I'm assuming that's expensive compared to cameras and software.
This is one of the big points about laser Doppler vibrometry. It's amazing technology. You shoot a laser at something, or you shoot a laser with several points at something, and however the light gets refracted, it's measured, and then it's visualized what vibration it is. This is touch-free, so you're not changing the object, which is a big advantage. But again, it's not really easy to use. It's a bit complicated software-wise and setup-wise. There's some limitations, and those vibrometers are not exactly cheap.
Yeah. So in terms of the camera systems that you can use WaveCam with, from what you've said so far, it almost seems like you can use it with anything. But what are there some limitations to what you can use it with in terms of hardware wise? Like, is there a certain protocol that it works with sensor data wise?
Yeah, there is. I mean, hardware-wise would refer to the camera, and we nearly have no limitation with cameras because we work
Okay.
with all standard formats. But of course, there is a certain limitation, especially in the frequency range you can look at. High-speed cameras have different ranges, and we've been measuring with data up to, I think, I've been working up to 10,000 frames per second, so that allows us to go to 5 kilohertz, which is already pretty decent.
Yeah, because that's like way into the audio spectrum.
Exactly.
So,
We're already in the audible spectrum there. Above that, it gets complicated because then, first of all, to generate a video gets really complicated. You generate a lot of data. And for the video itself, you need super good light conditions because the exposure time of each single frame is so small that, you really need good lights. You really need a good camera as well to be able to do that. So much higher than that kind of gets complicated. And also data-wise at a certain point, because the files get really big of those videos, we might reach a certain limit in the software. So with the cameras we had at hand, we tried the maximum, but around 10,000 frames per second video-wise is what we tested so far. So
cool.
I would say the really high frequencies definitely is a limitation. For example, laser vibrometer has no problem with going up to 20, 30 kilohertz as far as I understand. So at one point, I think that method will simply not work. And there's one other thing, as this method is optical method. So what it does is it's tracking pixels in the video. So it kind of grabs a certain point, tracks it over time, and by that can generate that, can find out about the displacement, about the vibration. So you need to have optical references on your object. In many cases, like an engine, like brake disc, for example, again, you have enough references because there's holes in the brake disc, and they are equally distributed, so it's super easy. You don't need to do anything. If you have a homogeneous surface, like a wall or like a simple metal plate or something like that, there is no pixel movement, so to say, because it's homogeneous. And then, of course, the algorithm cannot track any pixels, so you need to have optical references. So in some cases, that requires to do some preparation of the surface. Like, with a steel plate, you could spray paint something on it, or put some tapes on it, or put a foil with a pattern on it. Then you can easily do it. If you have a homogeneous surface which you cannot treat for any reason, like for example it's extremely hot or something like that, then that would also be a limitation. Of course, we need to have information, and our information is optical information and change of optical information, so we need to have some references.
So I guess WaveCam software probably works best with more complex images than the simplest images in that case.
Actually, yes,
yeah. But still, you're going up into the audio range in terms of being able to measure vibration. So that's incredible. So, for example, if you were to take a picture of a drill or something like that, I guess could you see where the motor is in the drill, because that would be.
We would see where the most displacement happens. I assume, and of course you can relate it to frequency. So you have a frequency distribution, you see a few peaks, and I guess one of the peaks probably would be the motor, which somehow related, I guess, to the RPM. So I would assume yes.
Cool,
I've not measured it.
Nice. I'd love to take a picture of a piano. That would be really fun.
We did measurements on a violin, not on a piano.
Oh, nice!
But one of the colleagues in the R&D is playing the violin, so he did a measurement, plugging the different different, how's it called?
Strings.
Strings, yeah.
Yeah.
And you could clearly see exactly how the violin was tuned, because you could see, okay, this one is vibrating at that frequency, which is okay or not okay or something like that, and you could
Cool.
differentiate those strings.
Cool. And in terms of the amount of data you can get from each pixel, because obviously not everything's vibrating at a sine wave. There'll be things vibrating with other waveforms, so you'll see overtones. Do you get the overtones as well?
Yep. What happens basically is that that the algorithm takes the video, tracks those pixels, and the result will be actually a map of virtual sensors.
Okay.
So you could imagine like putting thousands of virtual little vibration sensors over the whole area you're looking at. So we have the time data and we have the frequency data of each of those points. So we do have all the information like it would be real sensors.
Cool. So in terms of if someone was, if an engineer was looking to use WaveCam, what is the host system that they need to run this software on? Is it a PC, or can they use it in an industrial or an embedded setting?
It's a normal PC. We recommend, I think we recommend to have a graphic card, but other than that, normal PC. And then it depends on how much time you have. If you have a very old PC, then of course it takes a bit more time calculating.
And also in terms of like trial versions of this, what do you guys offer?
Yeah, it is possible to. There's two ways. So what we do if somebody wants to test it out, we offer them to send us a video and we analyze it, because we just need the video. And of course, it is also possible to send out like trial versions. We have different license systems, so you can have a license on a USB dongle, or we can put a license on a PC.
Okay, cool.
And we can change the time limitation so that we're pretty flexible.
Cool. So I think that's been a really good introduction to WaveCam. I also see that you do, or I might be wrong, but a hardware camera version as well that has like an array of microphones and then a camera sensor.
Yeah.
I can't remember which one that one's called.
This is called the Acoustic camera.
Oh, yes.
So it's a complete different technology.
Yeah.
It's kind of an old technology, I would say, because we've been doing it since nearly we brought it to market as the first company worldwide in around 2000 or 2001, I think. So, it was a bit before I started, so I'm not 100% sure. And what the acoustic camera does is there we visualize sound. So as you said, it is an array of microphones. So a certain distribution of microphones could be ring, could be spiral, could be something three-dimensional, depending on what you want to measure. But it's always an array of a high number of microphones combined with an optical camera. And with that, we visualize sound. So the sound is recorded. The algorithm is called beamforming, delay and sum beamforming.
Okay.
So it's a method based on looking at runtime delays. So when does the sound reach the first microphone, the second, and so on. And with that, we can calculate an acoustic map, which is basically only a colorful map. And this normally is overlaid over the optical image, so of the optical camera from the array. Or over a 3D model, that's also possible if you need some interior measurements or want to have more precision in something you measure from around.
Cool. So you guys cover, like, if we count the sound as vibration, which it effectively is, vibration monitoring from 0 all the way up until the
until ultrasound.
Until ultrasound. Cool.
Yeah, the microphone. So with our analog systems, we sample with 192 kilohertz. Okay. So that allows us, theoretically, to go up to 96 kilohertz. The microphones, go up to 60, 70 kilohertz, something like that. but it's already
Yeah.
pretty much in the ultrasound range.
Cool.
So yes, you're absolutely right. We cover a pretty wide range of frequencies.
So for the acoustic cameras, what application areas do those cover? And I guess you still got the benefit that they're non-contact, so you're not affecting the weight or vibration pattern by affixing anything. So this is incredible. So
Exactly. Yeah. The sensors we work with is microphones, so you're not changing anything.
Yeah.
And yeah, sounds a little bit like what I said about WaveCam, but there are also not so much limitations, because as I said in the beginning, we have different sizes, different channel counts, different geometries to cover a wide range of applications with that. And like typical applications are of course R&D related. So you have automotive, you have aerospace, you have energy, you have machine building. Wherever you have parts or consumer goods is a really big example of really big customer base for us. Wherever you need to find out something about the sound and wherever you might want to change something about that. Could be that it's too loud, could be that it has a certain sound that you want to change. It's like you do sound design. There, the consumer goods is a good example. Of course, also automotive, because you want to have the driver to have a good driving experience. Or you can find out something about the sound. So you do a measurement. We had one good example in a production place of Volkswagen. We did a publication with that, and they use the system for maintenance of their presses. You can imagine one of those big presses with those metal parts. And there they realized that the sound was changing a little bit, but the sensors in the machine could not fully indicate where the sound is coming from. So they used our system to pinpoint where it was coming from, and then easily could see what of the gears is about to break. It was still working, the machine, so they only exchanged that one gear or one gear set, compared to normally where they would have to dismantle the whole machine, look at all the gear sets, find the broken one, and then put it back in together, saving a lot of time in machine downtime and of course in material. So that could also be an example that you find out something about the sound. But to answer your questions, there's not so much limitations. So we measured, mechanical parts. We measured, we did room acoustics. We did structural acoustics of building or bridges or something like that. We do transportation of railway pass by, for example. And we also have done a lot of things in zoological applications.
Oh, okay, cool.
But, from time to time, we get those requests, mainly from university or research, whether we could measure a certain animal. So we measured insects, we measured bats, we measured elephants, frogs in the jungle, to like those small frogs who are really loud, to localize where they are. So there's a lot of different applications, and some of them are really interesting.
Nice. So with the Volkswagen one, is that something? Do they have an acoustic camera like kind of just always there, or is it something that you kind of brought in?
They have a couple of systems, but the one I'm relating to is exactly it's like a maintenance team which works in production, and they have one. Or actually two different, I think, different versions.
Yeah. Whereas the WaveCam software, you probably, if it was on an assembly line, you would just probably keep it there as part of the system, or
that depends on how the customer is doing it. But actually, normally they really rather go there when something is changing and then place the camera there and then do a measurement. Optimum would be, of course, to have one version of a video where everything is fine, and then another one when it's changing, so then you can compare both. But in reality, most of the time it will rather be like, something's changing with that machine, we quickly need to do something. Cool. So then that will happen.
Nice. So you do see people kind of using it in a way where it's monitoring something, and then when something's not normal, then they'll go and investigate, rather than them having to figure out that something's not normal and then go and
Yeah.
yeah.
We don't have anyone who's doing really monitoring. It's right now it's really rather used for troubleshooting when something is happening.
Okay, fair enough. Okay,
Yeah.
that makes sense.
Because otherwise, I guess for big machines that would maybe work, but you just need a lot of cameras for stuff like that. Then. So normally it's easier to go with one camera and then do different positions, something like that.
Cool, nice. And if someone were to approach you about the acoustic camera technology, what's the best way of demoing that?
The best way of demoing something is always, of course, on whatever the customer wants to measure. Because
I guess with that one, you have to be there, rather than the other one, they can send the video over.
It's impossible in that case. Yeah. I mean, we do have a lot of, as we've been doing it for 25 years, we have a lot of data, we have a lot of measurement data. So most of the time we do have something comparable already measured a while ago. So in many cases, we can just show something which is comparable to what the potential customer wants to do. But also there are some cases where we simply don't really know whether it works or not, or how well it works. So then we have to do a test measurement, have to do a demo measurement. Cool. And that, as you said, really requires us or one of our partners to go there with the system, do a measurement, look at what happens, and then,
Nice. Well, I think that's been a really, really nice introduction to what you guys do at gfai Tech. So thank you so much, Benjamin, for joining us. I'd say to any of the ipXchange audience, if you're looking to measure sound or vibration from basically DC to ultrasound, gfai Tech has got you covered. And very, very interesting technology that I didn't realize was there yet. So thank you so much for sharing it with us.
Yeah, it was my pleasure. Thank you very much.
Yeah, thank you very much, Benjamin. And looking forward to see if you share any new demos of this technology, because the animal ones particularly will sound like they may be quite amusing.
Absolutely. There will always be, as we are so connected to the research, they are always working on something. They're always working on new stuff. So it is definitely worth checking our homepage or going on LinkedIn, where we always post some stuff. There will be some interesting things coming out, I can guarantee.
Cool.
Thank you very much.
Cool, thank you.
Hey, where my engineers at?